Hi, welcome to my YouTube channel. This is GCT Tutors. This video tutorial is the part 2 of electric circuit. Please remember to like and subscribe, and also turn on your notification button for my subscription videos. Alright, without wasting much of our time, let us start. Okay, we have question 2. Alright, let me read question 2. We have very straightforward. Figure 8.1 shows 2 electrical circuits. We have circuit 1 and circuit 2. Alright, the batteries in circuit 1 and circuit 2 are identical. Alright, that's good. Put ticks in the table below to describe the connections of the two resistors P and Q. We have to tick either circuit 1 is series or parallel, and also circuit 2 either series or parallel. Okay, now remember in my previous video I tried to differentiate between a series circuit and a parallel circuit. Now for this very particular circuit here, this is a series circuit. Now for series circuit, just only one thing that you have to note: the current or the electric charge has only one route or path to flow through. I say that again: the electric charge or current, it has only one route to flow through. There is no other route that the electric charge can flow through. It's only one route. Now remember, let's assume that this switch is closed. Conventional current will flow from the positive to our positive terminal. This negative, it flows like this. We assume that the switch is closed. So as you can see, throughout this circuit, the electric charge or current is just flowing in one route. We don't have any other route. So that is a series circuit. Okay, let's come to circuit 2. We also assume that all the switches are closed. Now we know that conventional current flows from the positive terminal of the battery to the negative terminal. So also this continues to flow in this way. But on getting to this junction here, this electric charge has two routes to flow through. It can flow through this route, another one can flow through this route. So because we have two or more routes for the electric charge to flow through, that is why this is a parallel circuit. I think that's clear. So circuit 1 is series and circuit 2 is a parallel circuit. Okay, question 2, that's the B part. The resistor P and Q are used as small electrical heaters. Okay, we have to state 2 advantages of connecting them in circuit 2. Okay, all right, remember I just said something now about circuit 2, that this is a parallel circuit. So what our question is asking us is the advantages of connecting electrical components in parallel connection, in parallel circuit. Okay, now we are assuming that these 2 resistors, they are electrical heaters now. Okay, so one of the advantages is, number 1, the 2 heaters can be switched on and off independently. I say that again: they can be switched on and off independently. They can be switched on and on independently because the 2 resistors or the 2 electrical heaters, so to say, now they are connected directly independently to the power source. They're connected directly independently to the power source. It means that they can be switched on independently. Okay? And also another thing is that if one of these electrical components is faulty, let's say one of the heaters is faulty, the other one keeps on working because why? They are in parallel connection. Another advantage is that these two heaters now, they get full voltage from the power source because they are connected independently to the power source. So they get the full voltage, full brightness from the full voltage from the power source. So any of these three is okay. So let's write the first one. The heaters can be switched on and off independently. They can be switched on and on independently. That's the first one. The other one is that they get full voltage from the power source. And I also gave one that if one of the components is faulty, the other one continue to work. Any of these will first show the 2 marks. I think that's straightforward. In circuit 1, the ammeter reads 1.2 ampere when the switch is closed. Calculate the reading of the voltmeter. Okay, we are given I and we are asked to calculate V, the reading of the voltmeter in circuit 1. Okay, let's go back to that circuit 1. Now, this is the ammeter and we are told that it reads 1.2 amps. So we are asked to calculate the reading here, Okay, remember again that this is a series circuit. Remember that. Okay, because it's a series circuit, now we have to note the total voltage, but we don't know which is this. All right, but there's one thing that we can do, because I know that I have the total current flowing in this circuit. I can find the combined resistance of these 2 resistors. Once I know the combined resistance of the 2 resistors, then I can use that to calculate the voltage. All right, so we go back now. So we have the combined resistance. Let me call it R total, because this is a series circuit. So we just add the 2 resistance together, equals 4.0 ohms plus 6.0 ohm. So the combined resistance of the 2 resistors will be 10.0 ohms. And also we know the total current flowing in that circuit, which is 1.2 amps. So with these 2 parameters, we can calculate the voltage, the reading of the voltmeter. So we say voltage equals current times resistance according to Ohm's law. So the voltage equals the current 1.2 multiplied by the resistance, the total resistance or the combined resistance of the 2 resistors, which is 10.0. Okay, now when we multiply that, we see when we multiply by 10, we move our decimal to the right only once. So the decimal move like this once. So we have 12.0 volts as the reading of the voltmeter. All right, let me say that again. Very simple. We know the total current flowing in the circuit to be 1.2 amps. Then because this is a series connection, we try to find the combined resistance of these 2 resistors. And because it is series, we just add direct. So 4 plus 6, that gave us 10. Then from Ohm's law, we know that voltage equals current times resistance. So the voltmeter reading will now be the current which is flowing inside the circuit, which is 1.2 amps, multiplied by the combined resistance of the two resistors, which is 10.0 ohms. And when we multiply that, we have 12.0 volt. So obviously the reading of this voltmeter now will be 12.0 volt. All right, I think that's clear. So the reading is 12.0 volt. Okay, the next question: the two switches in circuit 2 are closed. Calculate the combined resistance of the two resistors. Okay, we also go back to that. All right, we're told that these two switches here, they are closed. They are closed. Sorry for that. I hope we are not offended. Okay, so I want to calculate the combined resistance of these two resistors, 4 ohms and 6 ohms. Now, because this is a parallel connection, the combined resistance is given by the formula R total combined equals the product of the two resistances that we have divided by the sum of the two resistance of the two resistors. Okay, just look at how many resistors do we have here. We have two resistors. Look at their resistances one by one. This one 4 ohms, 6 ohms. Multiply them, divided by the sum of the two resistance. Do you understand? Which is R plus. So we have R total equals R1. I can assume R1 to be 4 or 6, anyone. So we have 4 plus 6. Sorry for that. That's 4 times 6. Supposed to be 4 multiply. So we have 4 multiplied by 6. Oh, why this? Sorry. Okay, 4 multiplied by 6 divided by the sum 4 plus 6. So we have R total equals 24 divided by 10, and that is 2.4 ohms. Okay, let me say that again. Now, anytime we have a parallel connection and you want to find the combined resistance, let's say I have this. Let's say we have this simple circuit. Okay, and each of these lamps, they have their resistance to be R1, R2, and R3. If I want to find the combined resistance of these three resistors, to just be R total equals how many resistors do we have? 3 resistors. Add all their resistance together. We have R1 plus R2 plus R3. Then at the top, for the numerator, multiply all the resistances together. Okay, that's how to find out. Okay, so having said that, so the combined resistance of the two resistors will be 2.4 ohms. Okay, that's clear. We can continue. The E part: when the switches are closed in circuit 2, okay, the ammeter 1 reads 5 amps and the ammeter 2 reads 2 amps. Calculate the current in P. Okay, in circuit 2, we're told that ammeter 1 reads 5 amps and ammeter 2 reads 2 amps. Ammeter 1 reads, okay, let me erase this part so that we can see very well. Okay, all right. So we are told that this ammeter 1 reads 5 amps, 5 amperes, and the ammeter 2 reads 2 amps here. So we have to calculate the current through this resistor. resistor P. Okay, we assume that this switch is closed. Okay, now remember that we're told that circuit 1 and circuit 2, they are identical. The batteries in circuit 1 and circuit 2 are identical, so to say. Sorry for that. The batteries in circuit 1 and circuit 2 are identical. So if the voltage here, if the EMF of this battery here is 12.0 volt, that means the EMF of this one also automatically will be 12.0 volt. We got that from this statement because the batteries in circuit 1 and circuit 2 are identical. Okay, now having said that, we have also established that in parallel connection they have same voltage across the electric component but different current. That is why we can see that we have branches. You can see there is current of 2 amperes flowing through the 6 ohms, but there's going to be another current flowing through the 4 ohms, and there's going to be combined current flowing through the entire circuit, which is the 5 amps. Okay, if this is parallel connection and I just said that they have the same voltage, that means the voltage across this resistor P also will be 12.0 volt. Okay, I think I'm getting that. So we are looking for its own current. Let's call it I1. Now we know that from Ohm's law, voltage equals to current times resistance. So current equals to voltage all divided by resistance. The voltage is 12.0 volt and the resistance is what? 4.0 ohms. I think that's clear, so we can use that. I have 12.0 divided by 4.0, and if I divide that will give me what? 3 amps. Very interesting answer. What did you notice about that? You remember in my previous video I told us that in any parallel connection, the total current flowing in the branches must equals to the what? The current entering all those branches. The total current flowing through the branches must equals to the current entering all those branches. So if you look at this circuit, the 5 amps here, which is the current that is flowing through the circuit, when it gets to this junction, is split into 2. We have one passing through this route, the other one passing through this route. This other way that we just calculated, we got 3 amps, and the other one 2 amps. And on getting to this junction here, the 3 amps and the 2 amps here, they merge together to form the 5 amps. Remember, conservation of charge. Okay, so having said that, we can now write the final answer. So the current flowing through that resistor P will now be current equals the voltage across it divided by its resistance, which is 12.0 volt divided by its resistance is divided by 4 amps. Okay, divided by 4.0 ohms. Okay, so if I divide that will give me 3.0 amperes. That was how we got that. Okay, I think that's straightforward. So the next question, the power supply to resistor Q. The power supply to resistor Q. This resistor Q. We are asked to find the power supplies to this resistor Q. Okay, remember that the current that is flowing through resistor Q is 2 ohms and its resistance is 6 ohms. Okay, let's write that out first. We know that the current is 2 amps and its resistance is 6 ohms. Okay, the resistance is 6 ohms. Okay, so with that we can find the power. Now power equals the current multiplied by the voltage. But in this case here, we are given only current and resistance. That means we can still simplify it. But remember from Ohm's law that voltage equals current multiplied by resistance. So if I put the value of voltage in this formula here, we can see that power equals I multiplied by I times R, which is I square R. I think that's clear. So from there we can now say that the power equals the current is 2 amps, which is 2 square, multiplied by the resistance is 6 ohm, which is 4 times 6. 4 multiplied by 6, that is 24 watts. Remember, this is power, 24 watt. 24 watt. Okay, so the answer here is 24 watt. And the last but not the least, okay, it's been a lengthy question. The energy transformed in resistor Q, the same resistor what? Q, okay? Energy. Now remember that energy and power, they're related. We know that power equals energy over time. Power is the rate at which work is being done. Okay, so from here I can cross multiply. Energy equals power times time. Okay, power multiplied by time. But we just got power for that, and we have been given the time. Remember, always you work with SI unit. If this is in minutes, you have to convert to seconds. Okay, but because it's in seconds already, I can calculate my energy from there. So energy transformed in resistor Q will now be the energy equals the power supplied to Q, which is what? 24 watts, multiplied by the time, which is 300 seconds. So the energy equals, so if I do this, that is 12,6700. Now because it's energy, remember the unit of energy is joules. So the answer is 7,200 joules. Sometimes you might want to write it in what we call a notation form. Remember that 1 kilojoule is equivalent to 1,000 joules. So we can divide this. If I divide this by 1,000, 1, 2, 3, this is also equivalent to 7.2 kilojoules. All right, I think that's the end to this question part 2. I'm going to do the part 3 in my coming video. Please, if this video has really helped you, remember to like it, subscribe, and also turn on your notification button for any subsequent videos in the nearest future I'm going to release. Okay, before we go, let me quickly do a recap of everything so that I have a better understanding. We said that this circuit, it is a series circuit because why? We only have one route or one path for the electric charge to flow through it. But in this other circuit too, it is a parallel circuit because there are 2 or more routes or paths for the electric charge or current to pass through it. That's the reason why we're able to identify that circuit 1 is series and circuit 2 is parallel. We also talked about the advantages of parallel and series circuit. We said in series circuit, one of the advantages of series circuit is because it is economical. It is economical, so to say, because we don't have too much of wire to buy under series. It is economical, but it has a lot of disadvantages. One of the disadvantages is that when one component is faulty, the other component also stops working. So if, let's say, this component P is faulty, Q will never work again because they are both connected together. in just only one single loop. Okay, but in parallel connection, if one component is faulty, the other one continues to work. And also in parallel connection, all the electric components can be switched on and off independently, and they also get full voltage from the power source. Okay, and lastly, I also said that if you have resistors connected in series like this, resistor R1, R2 are connected in series, and you have to find their combined resistance. Because they are connected in series, just say combined resistor equals, just add all the resistance that you are given. But if they are connected in parallel, okay, like this, to find the combined resistance, look at how many resistors do we have? 3. What's their individual resistances? Multiply it together. If it is 1 million resistance that we have, multiply all together, divided by the addition of all those resistance. Okay, and remember the unit of resistance is ohms, and the unit of current is amperes. And I think with that, I am going to stop. God bless you. Remember to like the video once again and subscribe and turn on your notification button. Bye.